So the last speaker today was just step instead of the method. So the title is correspondence motions and the families of Nebis groups.
Okay. First, this talk really should be given by Mitra, but he hasn't said any speak. So he asked me because we have a joint work with Shiga and Riemann. So I tried to give his talk, but he gave me his slides with 21 page, and he asked me must be used for 45 minutes. So he delayed for dinner, blaming on me. So anyway, so I will try to talk a little bit slow, right? So first, the title is called Time Quasi-Conformal Motions and the Family of Mobius Groups, right? Okay, here's. So first, I think the one Mitra was a PhD student. I think gave him this paper, asked him to read. So this paper influenced him a lot. So this work is published by Beers in 1986, almost same year like he and Royden published the paper on holomorphic motion. So that paper also has certain connection with the holomorphic motion. So the paper is a holomorphic families of isomorphism of Mobius groups, which published in Kyoto University Journal of Math of Kyoto University. Is okay. So the main theorem of that paper was generalized by extension of a holomorphic motion and holomorphic family of Mobius groups by paper Mitra and Shiga in 2010. I think that is part his PhD, right? His thesis is in his thesis. This part, this work, the joint work with you, is also part of his thesis on it. It's after his PhD.
Who is he?
Mitra's thesis. No, not okay. You don't know. Anyway, so his thesis basically is this universal holomorphic motion things, right? Okay, so the main result in this talk is analog of Beer's result for time quasi-conformal motion. Actually, in the original, we started this one and quasi-conformal motion. But as I just said in my talk, we first finished this paper about the quasi-conformal motion analog to this Beer's paper. Then we found one of the driver forces for he kept asking, said, okay, make a more precise definition of a statement. So then we studied this analog paper for holomorphic family of isomorphism of Mobius group by Beers. We tried to analyze the same thing for quasi-conformal motion. But later we found that this counterexample, we actually developed a whole thing for time quasi-conformal motion. Then we correct everything we publish under assumption of time quasi-conformal motion. So basically his talk is tell us what we do for under time quasi-conformal motion. So okay, first let's restart the definition. Actually part of things I talked already, but it's worth to review it again, right? So now the definition said, okay, E is a subset in the Riemann sphere. Let X be a connected Hausdorff space with a base point x0. A motion of E over X is a map from X cross E to the C, satisfied that at base point is identity. that base point is identity, right? Base point is identity. And then for all the x, and map this one is injected. So that is just motion, right? As I said, without any additional condition, as long as you move every point, right? You move every point just injectively. That's usually we call motion, right? Called motion. So now in this definition, we see that x is the parameter space of the motion phi. We will assume that 0, 1, infinity belongs to E, and that the motion phi is normalized. That means 0, 1, infinity are fixed points of the map, right? Phi x, right? For every x in x. Throughout this talk, we will assume E is a closed subset of C hat, and 0, 1, infinity belongs to E. And the reason is we can assume that as long as you add a holomorphic condition or quasi-conformal condition or type quasi-conformal motion, you always can extend the motion to the closure of E. So that means you can always think that is closed subset. Because for the closed subset, you can define tabular space, right? Because for closed subset, your complement is open domain. So for each open domain, you can define the tabular space that you product together will be tabular space. So also, like E is subset of E hat, then phi from x cross E to C hat, and phi hat from x cross E hat to E C hat be two motion. We see that phi hat extends phi if that restriction of phi hat on the E, on the xe is the same, right? Equals phi. So that's the extension. Actually, in my talk, I didn't really give all this definition, but now you can see that's the definition. Means extension means restriction will be accepted, right? So that's the extension. So okay. So now I think that is clear, right? Shouldn't be a problem. Okay. So now the definition 2. Oh, that's very. Okay. Let's see. Definition 2 said, okay, for any motion, right, and any quadruple of the distinct point A, B, C, D of point in E, then like this one actually is the image, right, denote the cross ratio of the value, this 4 point, right, 4 point, phi xa, phi xb, phi xc, and phi xd. Then you can write this one as this one for x in x and E in the z. So now you can define the cross ratio of 4 points, right? Because the map is injected. You gave it 4 different points. The image also 4 different points. Then you can for only 4 different points you can consider as a cross ratio, right? Cross ratio. So phi xa minus phi xc times phi xb minus phi xd. Phi xa minus phi xd actually is well, but if you draw the picture, usually you draw the picture like this, and that's cross ratio, right? Cross ratio. So for every x, right, it is obvious that okay. First, if you look at it, because 4 points are different, this number cross ratio is in the C minus 0, 1, infinity, right? Because they cannot take 0, 1, infinity because 4 different points. So that is clear for in general calculation, right? So now you can think this is a point in the twice-punctured sphere. So then you let the rho be the Poincare distance around the twice-punctured sphere, right? So now, so in the paper extending holomorphic motions, that's the paper I just mentioned in the Silent First in 86, which is actually this paper appeared in the same journal same issue as Beers-Royden. I think Beers-Royden paper called a family of holomorphic maps, right? But so then this one in this paper, right, extending holomorphic motions, Ackermann in 1986, Sullivan and Thurston introduced the following definition. So definition 3 said, okay, a quasi-conformal motion is a motion first, right? That's a cycle 1, 2 of E over X with following addition properties. So that means for every X in X, every epsilon bigger than 0, there exists a neighborhood, right? So that then, so here's X. So you have a neighborhood here. So for this neighborhood, the cross ratio. Let's see. So this is X. This is neighborhood. For this neighborhood, the cross ratio mapped to the transpunctured sphere, right? Then phi X, right? A, B, C, D, right? Then you for that basically said this cross ratio is continuous, right? In this transpunctured sphere. So that means you have a neighborhood here such that for any quadruple of distinct points, you have this hyperbolic distance of phi y, ABCD, phi y prime, ABCD less than epsilon for all the y and the y prime in the UX, right? So if that map is quasi-conformal, you definitely have that, right? So, but this was a little bit weaker condition than quasi-conformal on the whole sphere. So that is basically the definition which also I suppose gave in my talk, but I actually asked him to define or to give all definition here. So now recall that homeomorphism of C is called normalized if it fixes 3 points, 0, 1, infinity. So now we use the MC to denote the open unit ball of the complex Banach space L infinity C. Each mu in MC is called Beltramian coefficient of a unique normalized quasi-conformal homomorphism, which denoted as W. This notation basically is followed from Arthur Spears' paper, right? We use W mu means a unique quasi-conformal mapping which fixes 0, 1, infinity, whose Beltramian coefficient is given mu, right? So that is 1-to-1 map, right? 1-to-1 map. So then the base point of MC is actually 0 function. So it was proved in the paper, which is Mitra's paper, is called extensions of holomorphic motions to quasi-conformal motions. Actually, I think that is a part of his thesis, right, published later. That he showed that properties that a motion proposition is motion phi x cross C is quasi-conformal. So this time is defined a Hölder-Riemann sphere, right? Define the Hölder-Riemann sphere. A motion from x across Hölder-Riemann sphere to Riemann sphere is quasi-conformal if and only it satisfies the map phi x from C to C is quasi-conformal for each x. The map from x to MC that sends x to the Beltramian coefficient of phi x for each x in C is continuous. So that actually, so that's in my talk I just put a note. Actually, in his paper he actually showed a very detailed proof of this one. So basically, it's a quasi-conformal motion on the Hölder-Riemann sphere. It's really just like a continuous map from x to the Beltramian coefficient, and also for each x, then the phi is quasi-conformal. So something like a quasi-conformal deformation, that's what we are going to introduce for group later. So now the part 2 means that the map is continuous, right? So that is basically that's the property we actually used in the definition of the time classical motion. Right? But then in Earth's definition, he didn't use that one, but actually it's equivalent to that, right? So, okay. So here's basically. Okay, so now let's see the definition 4. Definition 4 said, okay, that X be a connect house of space with base point x0, and E be a subset in C, right? Definitely is, we assume contains 0, 1, infinity, right? Also closed subset, right? But he didn't say that it's closed, right? You can think it's closed. So a time classical motion, well, but in the definition you don't need the close, right? A time classical motion is a motion from x to E to C of E over x with addition property. So that's exactly the same like I just said before. Given any x in W, there exists a quasi-conform map here, and neighborhood nx, right? You have a neighborhood nx. Then you have a quasi-conform map from C to C, and also you have a local quasi-conform motion from neighborhood of x across C to C, such that this motion equals this psi compose this quasi-conform motion. So this definition, I still think this definition is better than our original because you do not use that map of diatromic coefficient. You just use because if you use the diatromic coefficient, then you have to know the proof of the proposition 1 we just said in Dmitri's thesis. But you use that definition, you don't need that one. But it turns out these two definitions actually are equivalent. So the following was proved in the Geometria Shiga Wang's paper in 2018. Tahoto math said, okay, a motion is a time classical motion if a non-leaf given any x, there exists a neighborhood nx and continues g of x, nx to mc, such that phi yz equals w g x y, right? So that is basically our original definition for time classical motion. But if you want to make this definition is valid, you have to assume it's Dmitri's previous result, right? But the one given by Earth suggests us use that one because that will without assuming that, right? So actually, Shiga just told me we talk about this. They should have a good question to find a non-trivial time classical motion, which is not a holomorphic motion, which is not defined how to say. We gave a counterexample, which is not time classical motion. How can you construct such time classical motion on some closed subset, right? Actually, we don't have that example yet. Another thing is to find another if I non-leaf condition to see which motion is the time classical motion, right? So we have an example which is not, but can you find some similar condition to make that is? So now the definition phi said, okay, let phi from x cross E to C had let it be a time classical motion. Now we come to the group action now, right? That is the key point he will talk on the group action. Let G be a group of Mobius transformation, and suppose that E is invariant under G, which means that for every element of G, small g, the GE is still mapped to G, right? So for every G in the group, that means this group preserve the cosine, right? That's we call the G is G invariant. So now we see the phi is G equivariant if and only for each G in this group, every X in the capital X, then there exists another Mobius transformation which depends on X, depends on G, such that the motion, you originally have motion phi, which is from X to Z, right? Now you map with GZ, then that will be motion originally also mapped by Mobius transformation. So that is this one has to be equal to that one. So this is the Mobius transformation you find, right? So that is called a G equivariant motion, right? So that means this kind of motion, actually, if you look at basically you said, okay, if you have G inverse of Z composite phi G equals original phi, right? So basically, usually I like it write like this: phi equals here. Phi equals theta x G composite phi composite G inverse. But G inverse must be on first coordinates, right? Not on all things. So, but let's not write my one. But let's put on his original one. Okay. Here's another thing he asked me. He said, "You can give comments. Do not change my slides." So I will use my comments. Right? So now anyway, so that is G equivariant means, right? That means basically it's group action on the motion. So now let's say the definition 6 is like that G be a subgroup of the Mobius space of Mobius transformation, right? And suppose E is invariant and G, right? Isomorphism eta from actually this one is isomorphic means G to the image of that, right? So actually that's another thing. I asked him to send me the latex file. I said, in case I found a title. No, I don't have a title. So anyway, so that is another thing, right? But I searched the image of that. That's good. So that is said to be induced by injection, F, which is make F composite G equals eta G composite F of X. So basically, that's some kind of quasi-conformal deformation. So for all the G in the capital G and the Z in the GE, isomorphism induced by a quasi-conformal self-map of C is called a quasi-conformal deformation. If this map F is induced by, is actually is a quasi-conformal map, right? Then we call this deformation is quasi-conformal deformation of G. So now the definition 7 said, okay, let X be a connected Hausdorff space, and let G be a subgroup of PSL2C, a continuous family of isomorphism of G is such that first, for every X in the X, this one is actually isomorphism, right? Again, to this image, and the map is continuous for every G, right? This map actually is continuous from X into the group, right, as a continuous deformation. So that is called a family, a continuous family of isomorphism of G. Right, okay. So that is definition. So now statement of main result. That is the result actually we first proved under this quasi-conformal motion. Now we can prove under time quasi-conformal motion. So that statement of the main result is like this: that phi from X cross E to C had be a time quasi-conformal motion, where X is connected the Hausdorff space with a base point X0. That G be a subgroup of PSL2C, and suppose that E is invariant under G, right? So firstly, E is invariant. Suppose that for every Y, every G in the capital G in X, there exists a Mobius transformation such that this we just like define like this, right? For all the x, for all the z in the E and the G in G, then the conclusion is this one is a continuous family of isomorphism of G, and phi is a quasi-conformal deformation of G for every x, right? So originally we proved this theorem under quasi-conformal motion because the reason is if quasi-conformal motion can be extended to Hall complex C, then you can use that property to induce this theta x is continuous, right? Family of isomorphism, and also each theta x actually induced by quasi-conformal motion, quasi-conformal homomorphism. So then you have these two conclusions. So now we prove that one and time quasi-conformal motion. Okay? Any question on this theorem? Yeah, question? Yeah? You are one of others. You should ask a question. Right, so that basically means that under group action, they still preserve, right? Before, for this, in my talk, I don't have any group action on the E, but now it's actually on the group action. So that's actually Beer's original paper concerned about this family of moduli transformation and the family of holomorphic family of holomorphic maps. So okay, now let's see the okay. So here's in this proof we have to use that the following result that was proved by Geometria Shiga Wang paper, this 2018 paper. So that's that theorem A said let V be a simply connected host of space with a base point, and let phi from V to E in the C head be a G equivariant time quasi-conformal motion. Then there exists a G equivariant quasi-conformal motion phi tilde from V to C head, such that phi extends the phi. So in this theorem, you notice that parameter space V has to be simply connected, right? But if you look at this theorem, this X is just connected, right? So that's a little bit different, but it's not major different, right? But they do need to argue why simply connected can be go ahead to. So I think in our original paper for quasi-conformal motion, we also assume X is simply connected. But now we can even improve to connect. So, but even that is not a major improvement, but it still is one of the improvement. So now, what that this theorem means that for each x in V, the map of phi tilde x from C head to C head is a quasi-conformal motion, quasi-conformal map. That is a Beltramian coefficient be mu x. The map x to the mu x is continuous for x in V. The phi tilde xz equals phi xz for all that means the extension, right? For all xz in the V cross E. Then another is compatible, right? Phi tilde x composite G, composite phi tilde inverse x equals G, phi psi xg, right? That's so that's actually, so this one is just what I just want to write before, but actually is good. Means this under conjugate this quasi-conformal conjugation, which is still moduli school to moduli school, right? Okay, so that is. So now the outline of the proof of the main theorems. So first, okay, the outline of proof is this theorem, this one, this theorem, right? Outline of proof of this one. So, okay, so now outline of proof said, okay, we first discuss part two. Part two, that means that like X be a connected Hausdorff space with space point x0, and phi from X cross E to C hat be a G equivariant time-classical motion. Let omega be the set of all X in X with the following property. For each X in the omega, there exists a neighborhood such that theta t is a quasi-conformal deformation of G for every t belongs to the neighborhood of X. So clearly omega is open, right? Because for each t you have a neighborhood. So that neighborhood belongs to omega. So now you have to prove this omega is also closed. So if an open closed set in a connect set must be Hall space, right? It's non-empty. So clearly omega is open. Also omega is non-empty because base point is inside, right? So now you need to prove omega is closed. So now let K be a limit point of omega. Then you choose simply connect the neighborhood B of K, right? Now you have a limit point, and you take the neighborhood of limit point. In the limit point, at least one point is in omega. So that means you have this kind of property proved by theorem A. So now choose the simply connect neighborhood B. Then B contains a point P in omega. Since P is in omega, phi P is a quasi-conformal deformation of G. Choose P to be the base point of B. And like phi P equals E tilde, that basically change base point in the tangent space. I use that one to change base point. The previous base point is in the identity. Now you change it to the phi P actually. So now but the set also changed, right? E becomes E hat, E hat. So now the G also becomes G hat. So now you define another motion, phi hat from B cross E hat to C hat as following, right? So that's basically is change base point motion. That means before you have a T0 as base point, now you change to phi PZ as base point, right? Change X as base point. No, change P as base point. I'm sorry, P as a base point. You change P as base point now. Before the T0 is base point, now you change P as base point. So for every X in the B and Z in the E, then E hat is G hat invariant, right? Then phi hat is a time-classical motion of E hat over B with base point P. Then we show that theta X is a quasi-conformal deformation of G for each X in the B, right? So then you use that theorem we proved in Tahoko's paper. Then you can see that. Then K is definitely omega. So omega becomes closed too. So then omega has to be equals X. So now you can prove the one. So let's say if you look at the theorem, like a theorem, you have a one means it is a continuous family of isomorphism. Second is actually is the quasi-conformal deformation of G. Now we actually prove the second, right? Because the use is every point you have a simply connected neighborhood, and you just patch together, just like continuing underneath these things, right? So, but now you have to prove one. It means theta X is a continuous family of isomorphisms. So that one you also need a time quasi-conformal condition. So now for one, we need the following result. Where he said it is again in this paper, Tahoku paper, said okay, let phi from X to E in C hat be a time classical motion. For each Z in E, the map of phi delta Z X to C hat is continuous. Then we are given that this equivariant condition for all Z in the E, G in the G. Since E has at least 3 points, for each x in x and g is in g, the Morris transformation is completely determined by above equation, right? It easily follows that theta x is a homomorphism for each x in x. Then you need to show this phi is injected, right? Injected. So we show that theta x is injective, and hence this map is isomorphism, right? Well, how to show that phi x is injective, right? So we already know this is a homomorphism, right? That's because it's composition property. You know this is homomorphism, but now you have to show this injective. After you show this injective, that is isomorphism from G to this image, right? So now, how to show the injective? You choose 3 distinctive points, Z1, Z2, Z3 in the E. Then for all the x in the X, let Hx be the unique Morris transformation, such that this at 3 points they are agree as phi, right? Because we know every 3 points decide a unique Morris transformation, right? So then you have this equation, right, like this. For all the, now you just see that that for each I, the right hand side part, this hand side part depends continuous on x. Therefore, this x to here and x to here are continuous map, and so that is continuous. Oh, now this one is prove the continuity, not the injected. It didn't prove, I think. No, it didn't prove. But anyway, so injective is not a very hard proof, so he didn't say he proved that. So he proved that's continuity part, right? So that is actually choose 3 points. You make that agree. Morris transformation agree on 3 points. Then you have this thing, this equality. Then you show this one is continuous. This one is continuous, right? This one is continuous because this 3 points is continuous depending on x, right? So that is this Morris transformation continuous. But then this one is also continuous. So that implies this one is continuous, right? So right. So that actually. Right, okay, anyway, so now that is actually show that the first, I think it's the first part of the main result, right? Sigma x is a continuous family of isomorphism of G, right? So that is. What time now? So 5:45. What time is done? Like 5 minutes. 5 minutes?
5 minutes.
Huh? 5 minutes? Okay, good. Yeah, I have a lot to go. So, okay, so the main technique in the proof are some important properties of Titan space of closed set. We give an overview of this property. Okay, now this is actually the theorem is proved now. So he want to give some overview of this Titan space of T. That actually I didn't define in my talk, but he actually defined that. So now we said, okay, two normalized quasi-conformal self-map FGC are said to be equivalent if that FG inverse component G is isotopy to G. Then the Titan space is a set of all the equivalent class, right? So now you have this map of which projection, and this map is actually map every mu to the equivalent class. So that P actually is holomorphic. So now he said in his 1990 doctoral dissertation, Lieb proved that T is a complex Banach manifold such that the projection PE from MC to the T is holomorphic split submersion. So the complete details are given in the paper of Mitra's variation of modulus and holomorphic motion. So then definition 9, W is a connected complex manifold with the base point x0. A holomorphic motion of E over W is a motion of phi over W such that this one is holomorphic, right? So now then he defined the universal holomorphic motion. That's something I didn't define in my talk. He said that holomorphic motion is defined as W mu to Z, because this definition is independent of an equivalent class, right? So give 2 point in equivalent class, you get the same definition. So that then the definition of PE is guaranteed phi is well defined. It is a holomorphic motion since PE is a holomorphic split submersion of mu to the W mu. Is a holomorphic map from MC to C. I fix so that is actually he said the measurable Riemann mapping theorem is proved by is in the Alfred Spears famous paper, right? So now holomorphic motion. So he said now what is the universal holomorphic motion means, right? So now this holomorphic motion is universal in the following sense. Like phi from V cross E be a holomorphic motion where V is simply connected to the complex Banach manifold with the base point x0. Then there exists a unique base point preserved holomorphic map F such that this is phi is pulled back this capital psi of E. So pullback is defined like this, right? So now that is actually that's his thesis, but published in the journal Annals of Math. A similar universal property for time classical motion is proved by in our paper. So now it was shown that same paper that every holomorphic motion is time classical motion. Hence, phi E is also time classical motion, right? Here is a statement of universal time classical motion. Said okay, phi from V to the V cross E to C here is time classical motion. We simply connect the Hausdorff space with base point T0. Then there exists a unique base point preserving, well, that's one typo. Continuous map from F to V to T such that phi F star pullback equals phi. So now the classical motion in the sense of Simon and Thurston do not have this universal property, whereas time classical motion do have this universal property. That's similar to something I taught before. So in what following, we give a list of a basic property of TE that we use. There is a continuous space preserving map S from TE to the MC, such that the PE composed S is identity map on TE. So this S really is Dwyer-Earth called Dwyer-Earth extension. Actually, Ara mentioned in his talk. Every circle homomorphism you can extend as a classical motion into the disk which is compatible with the group action. That's called the Dwyer extension. From Dwyer extension, you can have a continuous section from TE to the MC, but you don't have a holomorphic section. So that's what he wants to say. So now the technical space TE is contractible, right? Because of this one. The definition 11. So the side of the map S from TE to MC is called the Dwyer section of PE for the technical space TE. The conformal neutrality of Dwyer extension was most fundamental in our work. We will state the basic result. Okay, so now, here's 2 more slides. Let's finish that. So as usual, E is infinite closed subset in C, and 0, 1 infinity belongs to E. So that G be a group of Mobius transformations such that E is invariant under the action of G then for each G in E, there exists a bi-holomorphic map from that's basically so-called base change map, right, from here to here, where G hat is unique Morgan transformation subset. G composes W mu G inverse fixed 3 point. For each G in G, rho G is base point preserved, right? So now so now the definition 12 says we define MCG and TEG as follows. MCG equals mu, which is compatible with every G in the group, right? So then TEG is actually all the mu, which is also have compatible with G. So then we define this group compatible diatropic coefficient and also a group compatible with typing space. Here, conformal naturality of the Euler extension is that S from here is cross continuous section. Then if T is here, then also is the cross section for this G invariant space. So basically, you have T E MC G, then you have a T E G, so that your section really is also T. So your section also is going to here, right? So going to here. Before you actually use T MC here to T E here, but now actually is group compatible. So now we also need the following result approved by in our paper here. So that phi from V cross E to C hat be a time classical motion, where V is a path connect the Hausdorff space with a base point. Suppose there exists a base point preserving continuous map F from V to the TE, such that F star pullback of universal harmonic motion becomes phi, then phi is G hypervariant finally F maps this V to the TGE, right? So that is actually is a group invariant version of a theorem I just told before. So now that he has a last remark said, okay, the conformal naturality of the Euler section is a generalization of to TE of a result in the foundational paper conformally natural extension of the homomorphism of circle by Euler paper in 1986. So all the paper is published in 1986. That's interesting. The details of this generalization are given in the paper of Euler section of homomorphic motions and some application by Riemann and Dmitri. So this paper actually gives a summary of a lot of results in this direction. But before 10 classical motion, mostly is homomorphic motion and classical motion. Okay, I think he forgot to see that. He forgot to thank you. Yeah, okay.
Other questions?